All right, so let's get started. All right, so the next chapter we're going to get into is hopefully pretty familiar to a lot of you. It's going to be about acid and base chemistry, which I know you covered in a lot of detail in Gen Chem. However, it's going to take a new spin in organic chemistry. So let's first talk about the two theories. And interestingly enough, both of these theories were developed in the same year. And they were both developed in about 1923. Does anybody remember the two main acid-base theories? Yep. Yeah, Bronsted-Lowry was the first one. And then you also mentioned Lewis, that chemist I talked about on the very first day. He was the one that came up with the other theory. So they're very, very similar theories, but they describe acid-base chemistry in very different ways. So how do we describe acid-base chemistry when we're talking about Bronsted-Lowry acids and bases? Yeah, movement of protons, right? So they exclusively focused on movement of protons. How did Lewis describe it? How was it different? Electrons, right? So he talked about movement of electrons. We'll talk about both of these theories, but for the first chunk of this chapter, we're going to focus exclusively on Bronsted-Lowry. All right, so Bronsted-Lowry acid-base theory is pretty simple. Do acids donate or accept protons? Donate. So acids donate protons. Hopefully we remember that from Gen Chem. Bases, on the other hand, accept protons. The way I always describe this is imagine that it's a track relay race. How many of you have seen relay races where they hand off a baton? Right? So in that relay, the runner behind hands off the baton to the person in front, and then they continue running, right? Same is true with a proton. One thing that drives me nuts in Gen Chem textbooks is they just show H+ floating around. That does not happen. That'd be the same thing as the baton in a relay race just floating around trying to find the next runner. Doesn't happen that way. It gets handed off. All right, so we like to show this in organic chemistry by using some special arrows. So over here, I've got my acid. And over here, I've got my base that I'll label B. And in this case, the base is going to be the thing that's going to be the runner behind. It's going to grab that proton. Do protons have electrons with them? No. So really what it's going to do is it's just going to grab only this side. These covalent pair electrons have to go somewhere, so they're going to get dumped on A. We normally show this with equilibrium arrows, with the exception of really, really strong acids and bases, which we'll talk about later. But now, whoops, let me keep it color-coded. We've got A with a lone pair, therefore it has a negative charge. The proton will be directly attached to B, which would have a positive charge. Does anybody remember how we would describe A with the lone pair and the negative charge in this situation? It's going to be a conjugate something. Conjugate base. Why isn't it going to be a conjugate acid? It lost its proton. It has no more protons to give, right? So it could only be a base. All right? That means that this must be the conjugate acid because it has the proton and it could potentially give it back to A and go in the reverse direction in this equilibrium. All right, so a few things we really, really have to remember is that strong acids or I should say strong acids result in stable conjugate acids or conjugate bases? Conjugate bases. So if you have a really, really strong acid that wants to give up its proton, we know that the conjugate base on the other side of the equilibrium must be something that's relatively happy and stable because it doesn't want to go in the reverse direction and steal the proton back, right? So concept that's really important. Conversely, strong bases result in stable conjugate acids. How many of you remember this from Gen Chem? That's good. This is going to be a key driving feature of everything that we do in this chapter. All right, but before we get too far into this, we want to define the equilibrium a bit more. All right, so I know some of you haven't taken Gen Chem in a while, so we'll just review equilibria for a second. Normally, when we're looking at an acid, we're mixing an acid with water, right? And when we throw an acid into water, we know that the water can steal this proton from the acid and give electrons to A. So just like before, we would have A with a negative charge, and then we would create H3O plus. What is H3O plus called? The hydronium ion, right? So an acid in water generically has this equilibrium set up. All right, so now what we need to do is we need to define KEQ. That's the quantitative measure of concentrations present in an equilibrium. So what would go on top? The products, right? So on top, we would say the concentration of that conjugate base times the concentration of hydronium ion over the concentration of our original acid times the concentration of water is going to be KEQ. And remember, this is large K, not small k. What's small k? Rate constants. We're not talking about rate, we're just talking about the end concentration after equilibrium has been achieved. All right? So what we can do is we can kind of look at this water concentration. The water concentration when we're looking at acid-base chemistry is really going to be constant. So what they often do is they say, all right, let's multiply both sides times the concentration of water to get rid of that unit. So if we multiply the concentration of water, it's got to show up on the left-hand side, and then it's going to disappear from the right-hand side. And we would still have HA on the bottom. So just doing some basic algebra. The cool thing is we condense this down into a new value that's just called Ka. So it's what we look at whenever we're working with acids. Yep. Yeah, so it's a good question. So you're asking about the equilibrium arrows, and you were saying if it's a strong acid, do we really need to show equilibrium arrows? We'll talk about that in a second. It really has to do with statistical probabilities, right? Technically, everything's in equilibrium. However, there are some reactions where the backwards path going to the left-hand side is like 1 in 100 billion jillion. So we just don't even show it. We just say it's a one-way reaction. Okay. Yep. All right, so Ka is going to be this equilibrium constant where we don't have water included because water is more or less held constant throughout this process. And this is a really important value in organic chemistry. Does this kind of sound familiar to everybody? Ka versus KEQ? Okay. It's important to remember that Ka is always going to be the acid dissociation constant. All right, so now I've got a more abstract question for you. Let's say we have a large Ka. What does that tell you about the acid? Is it a strong acid or a weak acid if you have a really, really big Ka? So large Ka is strong acid? Or small? Let's think about it. Some people get it flip-flopped. What do you guys think? Yeah, I would say large Ka is making more of the hydronium ion, right? We know the hydronium ion is a measure of acidity, so we can say large Ka must be a strong acid. Small Ka would be a weak acid. People often get these flipped when they think about pKas. How many of you remember talking about pKas? This is different from pKa. We're not talking about pKa right now. We're just talking about regular Ka. All right, so let's take a look at a couple examples. All right, so let's say I have hydrochloric acid, pretty good acid. We can have that mixed with water, and in this case, I'm going to show all of the bonds. In this case, water can steal the proton from hydrochloric acid, and we'll make the anion Cl-, meaning the chloride anion, and we'll make the hydronium anion. In this case, what we're looking at is the conjugate base. Does this look like a pretty stable conjugate base? Cl-? Should be. The ocean has a whole lot of Cl- floating around in it, right? Saltwater, Cl- is incredibly stable. So this is a really stable conjugate base, which tells us a lot about HCl. It means that HCl must be a strong acid, right? And in fact, we can measure Ka here. And we can say, all right, Ka is going to be the concentration of Cl- times the concentration of hydronium over the concentration of HCl. And if you look this up in a table, it's about 100 million. So it tells us this is an incredibly good acid. All right, let's compare this to another situation. All right, in this next one, we're going to look at methane. That's CH4, and water, just like before, OH2, or H2O, I guess. And we can imagine, hypothetically, what if water steals a proton from this molecule of methane? This would now be our conjugate base. Is that very stable with a negative charge? Why or why not? Let's think about negative charges. Where do they prefer to be? On electronegative atoms or non-electronegative atoms? Electronegative atoms. Is carbon electronegative? No. So this is relatively unstable, which tells us right off the bat, this must not be a very good acid, just qualitatively. However, we can measure it quantitatively, and we can say, all right, the concentration of our CH3 lone pair with a negative charge times the concentration of hydronium ion over the concentration of methane is going to be equal to about 0.000000000, and I'm not even going to draw it all, because if you count all the zeros in here, there's about 48 zeros. It's an infinitesimally small number, right? Which means it really, really doesn't want to give up that proton. In fact, the probability of methane giving up its proton to water is so small, it'd be like trying to hunt down one specific atom on planet Earth. You're just not going to find that specific atom. It's just out of the realm of possibility. So it's really not considered an acid at all. All right. However, you can see we're dealing with numbers ranging from hundreds of millions to billions, all the way to tiny, tiny numbers. That creates a big problem. What do we do to deal with the huge range of numbers? Scientific notation, or even better yet, log scales. Log scales work a lot better for dealing with this giant range. All right, so with that, we look at pKa. So pKa helps to narrow down this huge range of values. All right, so in math, does anybody remember what the symbol P stands for? Same thing with pH, pKa. Negative log. Exactly. So pKa is just an operation where you swap out the P for negative log, and it's going to be negative log of that Ka value. All right, and I kind of mentioned this before. If we have a small pKa, what does that tell us about our acid? Is it strong or weak? Strong. Remember, it flip-flops. That's the thing that really confuses students. If you have a large pKa, it must be a weak acid. All right, so let's go back up and look at the values, and we'll kind of switch them to pKa units. All right, so if we go back up and we look at this whole reaction with HCl, if we measure this, we could say that the pKa is actually going to be -8. So typically, anytime you're running into negative pKa values, you're looking at something that's generally considered to be a very, very strong acid because the negative value is quite small. All right, over here, this would be a pKa value of 48. That's really, really large. Once you're getting like into the 30s, you're looking at molecules that just don't want to give up their protons very much. But now we're dealing with a range from about -10 to 50. That's a lot more manageable to work with. All right, now the really, really important thing that I want to leave you with is the difference of one pKa unit. Is an order of magnitude. Meaning 10 times. Because oftentimes in organic chemistry with new students, I'll see them look up pKa values and they'll say, well, they're really close, they're only different by 2. It's like, yeah, that's like saying that guy is 100 times faster than that guy. It's a huge difference. We actually need to pay attention to these small values and differences, right? So pKa, even though it cleans things up, we have to be aware that small changes are very, very impactful and meaningful in the overall strength. Does that make sense? All right, so with your problem of the day, this is a little bit more abstract. I'm asking you, why would the conjugate base for one molecule be more stable than the conjugate base for the other? So I want you to sit down and think about that, and we might use some of the concepts that we've recently looked at. All right, hope that helps.